Hello everyone, welcome to recitation number 12, a dozen so far. And in this recitation, our focus was on even more decidable problems and reducibility. So let's just jump right into it. So in this first question, we actually did it last time. We need to prove that the complement of H1 is not Turing recognizable. So let's just go over what we said last time. So in this proof, it was actually interesting because the way that we'd usually prove something is undecidable, we'd say that or is not recognizable. We'd assume that it is, and we reach some sort of contradiction. But what they did here is, imagine you have like some universe of all sets. You're going to have H1, and you're going to have H1 complement, which is everything outside. So what they're actually going to be doing is they're still going to be assuming, yes, that it is Turing recognizable. But the way that they're going to be getting the contradiction, so they named the machine S is what recognizes this language. They're going to say, oh, S doesn't exist neither outside H1 nor inside. If it's not here and it's not there, it can exist. Because imagine this is your entire universe. S has to either belong to H1 or to H1 complement. So with H1 complement, let's focus on this part. M doesn't hold on M. So if H1 is the language where M holds on itself, the complement would be where it doesn't hold on itself. So in case 1, they're supposing that it is in the complement. So S is right here, outside. This must mean that S doesn't hold on S, right? Since we're saying S belongs to H1 complement, and H1 complement is simply the machines that don't hold on themselves, we can conclude, hey, S doesn't hold on itself. However, S is a recognizer for H1 complement. That was our original supposition. S is the Turing machine that recognizes H1 complement. That means S is the machine. You give it any other machine, and it'll be able to tell you yes if M holds on itself. We don't care about the no. We actually don't know about the no. But for the yes part, if this machine, doesn't hold on itself, so if M doesn't hold on itself, so on M, it will be able to tell you yes. S will tell you yes. Well, think about it. Now we're asking, hey, instead of feeding it M, we're going to be feeding it S. S doesn't hold on itself. Since S is a machine that doesn't hold on itself, S should be able to correctly tell you, yes, it doesn't hold on itself. But for that to happen, it would make S have to hold on itself. So review what I said like 10 times, and maybe it'll make sense. But the first piece of information is, oh, S doesn't hold on S. That's from this supposition. The other piece of information is that S is a recognizer. So if any machine doesn't hold on itself, S should tell you, yes, it doesn't. Those two pieces of information, they can't exist together. You're saying S doesn't hold on S, and then you're saying S should hold on S since it's a recognizer for itself. So it should be able to tell you, yes, I don't hold on myself, and there's like where the paradox or the contradiction happens. Okay, so that's for the first part. We just proved that this scenario does not exist. S can't be in H1 complement. So now we go to the other part. Well, does it belong to the other thing? So we said this part can't happen. What about it being inside of H1? So now we're supposing that S doesn't belong to H1 complement, which means S is in H1. This must mean S should hold on S, right? Back to the definition of H1. It's the language where a machine will hold on itself. So if S is in that language, then S should hold on itself. That's the first piece of information. However, we're saying that S is not in H1 complement, right? If it's in H1, that means it's not in the complement. And look what they do here. They're saying, oh, okay, since S is not in the complement and S is a recognizer, that must mean S doesn't hold on itself, which leads to a contradiction. Let's say that again. Remember, S is your recognizer. You give it some machine M, it'll be able to correctly tell you yes. Now, since they're saying that S is a recognizer and S holds on itself, then S won't be able to tell you yes correctly. That's fine. Or S won't say yes. Can we agree on this part? S is a recognizer. When we feed it S in this scenario, it's not going to say yes. Why? Because of this assumption. we're saying that S should hold on S. S will only say yes if the machine doesn't hold on itself. So it's not going to say yes because we're assuming S doesn't hold on itself. Now this is what they're saying. Oh, since S is the recognizer, that must mean it shouldn't hold on S. So they're saying that S is going to loop forever when it feeds itself. And there's the contradiction. Like, since S doesn't say yes on itself, then it's probably going to loop forever, and that's the part I disagree with. So the solution doesn't have to be correct, by the way. It's actually because there's a scenario where it might say no. So think about it. When S takes S, or any machine for that fact, it's either going to say yes, it's either going to say no, or it might loop forever. Why? Because it's only a recognizer, it's not a decider. So there's a chance it might loop forever. Since they're saying you're not going to say yes, then you're probably going to loop forever. That's what they're saying. Oh, S being only a recognizer shouldn't hold on itself, but that's not necessarily true. Because there's a scenario where it might say no. And in this case, saying no would just mean that S does hold on itself. Okay, so what's wrong with this proof? There's like two things. First, this part, not really necessary. I think here what they're assuming is, usually when you make a recognizer, all you care about is the yes part. Like if you make a recognizer for some language and you are able to correctly say yes, then that's it. You made a recognizer. You don't care about the no because you can't completely predict the no because of the chance of it looping forever. So here, all they're caring, I think in this scenario, they might assume that the recognizer is only going to say yes, and any other scenario just going to loop. That's not necessary. The way recognizers are defined, they might say yes, or they're going to say yes correctly. They might say no, or they might loop forever. So this part is wrong. And then even the way they defined H1 complement, it's not really all that good. Like what I care about is maybe this part is where we focused, but yeah. Like a better description for H1 complement would be either M is not a Turing machine or it halts on itself. Remember, because specifically we're saying H1 is the language that accepts Turing machines that halt on themselves. So if you're not in H1, two things. Either you're a Turing machine and you don't halt on yourself, or you're not even a Turing machine. Okay. That's everything outside of H1. And they didn't really describe it correctly, but that's okay. So this is just to let you know, hey, whenever you see a solution, don't just assume it's going to be correct. Think about it more of like a guideline. And it is interesting what they try to do here. But I don't think this idea of the proof works because of case 2, you can't really assume that it's going to hold, that it shouldn't hold on itself, that it's going to like loop. Okay, moving on to the next part. Show that if language L and its complement are Turing recognizable, then that must mean that the language L is decidable. Show that if language L and its complement are Turing recognizable, then that means the language is decidable. So go ahead and think about it if you have an idea what we should do here. But the idea is L is Turing recognizable. What does that mean? You have some recognizer called maybe R1 for the language L, meaning when you take in W, it'll tell you yes if W belongs to L. But its complement, it's also Turing recognizable. So if there's some, so we'll say R2 decides the other one, or is a recognizer for the other one, it's not a decider. It'll also take some string W, it'll tell you yes if W is not an L, or in other words, sorry, if it's, no, my bad, I did it in reverse. It'll tell you yes if W is an L complement. Right? It's a recognizer for L complement. So it'll tell you yes if the string or if the input belongs to the complement, which means it doesn't belong to like the complement of the complement, which is just the original language. Think about it. If you have these two recognizers, surely you could build a machine which is a decider, so call it D for decider, for L, where if you give it a W, it'll be able to tell you yes if W is an L, and it should be able to correctly tell you no if it's not. Just like a reminder in case you're not familiar, a decider is this thing on the right-hand side. A decider will be able to tell you correctly whether an input belongs to the language or not. It'll be able to tell you yes or no correctly. A decider. But on the left-hand side with our recognizers, notice the recognizer for R1, it's only able to tell you yes correctly if something belongs to the language. And our recognizer for the complement, it's also just going to say yes correctly if it belongs to the language. The no part, we don't have. Like here, do I have a no for the first one? Not necessarily, because I might loop forever. And same thing here. For the other recognizer, I don't really have a no. However, they do fill each other's gaps. You could use these two recognizers to build the decider, right? You could use them both. But how? Should we do it? So when I say how, there's two ways. Either we're going to do it sequentially or we're going to do it in parallel. If we do it sequentially, it's going to cause problems. So why? Let's make a new slide. And get this whole thing. So the question is sequential or in parallel. Think about it. Sequentially means you're gonna use one machine after the other. So say I get, or in parallel, say first I get W, and I decide to run it into my R1. And then after that, if it doesn't work, I'll feed it into my R2. Like if R1 says, doesn't say yes, if it says yes, then we just stop. But if it doesn't say yes, like if it says no, it doesn't accept it, then I'll feed it into R2. But like that's the whole problem. You don't know if it's gonna say no. If it does say no, you don't need R2. R1 would be enough. So if R1 says yes, great, you'll accept. But if it doesn't say yes, it might loop forever. And R2 might say, R2 might accept it. Okay, like if one machine loops on an input, the other one most definitely is going to accept it. So if it's looping on R1, you're never going to reach R2 and test it out. So sequential, it's not really going to work. Instead, you want to do it in parallel, which means, hey, do both machines at the same time. So you get the string W, just run both machines at the same time, like you have R1 here, and you have R2 here. Like we'll use a splitter, so like we'd have a multiple tapes of the same input. So W is being fed here, W being fed here. Whichever machine stops first, you'll stop. So if R1 says yes, which remember R1 is a decider for the language, it's saying yes, that W belongs to L. So outside you'll say yes, W belongs to L. If R2 says yes, W is in L complement, you'll fit that with no, W doesn't belong to L. Because if it, do you get it? Like if R2 is saying yes, I belong to the complement, that means, oh no, I don't belong to the original. Remember, we're trying to make a decider for L. So D decides L, and that's it. Okay, that's it. Let's just maybe write it a bit more formally. So we're trying to make, say, D, which is a decider for L. So we say, or let's say, let's let R1 and R2 be recognizers for L and L complement, respectively. And now we want to create D, which is a decider for L. So on input, W, where W is a string, let's say. Step 1, run W on M1 and M2 at the same time. What does that mean at the same time? One step on M1 and one step on M2. I called them M's, I meant R's. So R here, here, and here. Does it make sense? Like maybe we should go back for a second and talk about this whole parallel thing. Or maybe let's do it here. So imagine you have your R1 machine. It has its own version of W, which is like made up of zeros and ones. And then you have R2, which has the same initial W, say 0, 1, 1, 0, 1. And like they're both starting at the same place because not necessarily starting at the same place, but they do have the same string. So to run them at the same time and like run them one step each, R1 say begins, it does its thing, like it might change this 0 to 1 and it might move to the right, so now it's pointing here. You do one step, now you go to R2 and it does its thing, so maybe it sees the 0, it keeps it as it is, and it just decides to move to the left. Now I go back to here and this one does its second step, then this does its second step, third by third, fourth by fourth. You move them step by step each. That's how you get the idea of running them in parallel or running them at the same time. And when do we accept? Well, if R1 halts, that means, what does that mean? If R1 decided to stop, we should accept, right? So we accept, since like we've been saying all this time, that must mean W belongs to L. If R2 halts, we reject, since W belongs to L complement, so it doesn't belong to L. That's it. That's the definition of D, and yeah, maybe something like this. So we're running them in parallel. If one halts, you accept, or the other halts, you reject, and that's it. There might be this scenario, and the way that we did it, so this is maybe a bit more an idea of why they maybe messed up here, the solution. Like the way that we made our recognizers here, R1 and R2, if you focus on the blue part, you'd assume they only worry about yes. If there was ever a machine that where it's not going to say yes, it's going to loop forever, because we never took of the scenario of no. But it doesn't matter if we take care of it or not. All we care about is the yes part. But they could say no. Like if at some point R1, now here when I say halt, maybe we should be more specific, halts and accepts, and R2 halts and accepts as well. Because I don't want them to halt and reject. That would mean different things. Like if R1 halted and it rejected, we should actually reject too, because like it's saying, oh, it doesn't belong to L. They could say no, but not necessarily. They will definitely, when they say it, they will accept when they should. Hopefully that's making sense. Undecidable problems, which is the topic of today, so just a few more questions here. Consider the emptiness problem for Turing machines. M is a Turing machine and its language is empty. So this is a language where it'll only accept Turing machines if their language is empty. Like they're empty, they don't have anything. Now, what they're saying is show that ETM is co-Turing recognizable. If you haven't heard this term before, a language is co-Turing recognizable if its complement is actually Turing recognizable. Okay? Like ETM is co-Turing recognizable if the complement is actually the one that's Turing recognizable. Now note that ETM is this language. So what should we do here? What's the complement of ETM? It's the Turing machine where the language is not empty. Again, it's more than that. It's also the language where we might not even have Turing machines. Like M could not be a Turing machine, but we don't care about these parts. Like we try to make it a bit simpler by focusing on certain parts. I can't crop. Never mind. Okay. So what we care about right now is M is a Turing machine and the language is not empty. That's what we're trying to prove. And this is actually Turing recognizable. Why? So this means you'll accept the Turing machine as long as it at least accepts one string, right? So let's just dive right into it. Of course, you can pause and try to think of a solution if you want. But what we care about is the following. So we'll accept Turing machines. We will accept the machines as long as they accept at least one string. That's it. You have to come up with a method where maybe you check all the possible strings, and as long as that machine you're testing accepts one of those strings, you will accept. So say let S1, S2, S3, etc. be all the possible strings. So be all the strings in sigma star. So given some Turing machine M, if at least one of those strings is accepted by M, our recognizer should accept M. Okay? So if M accepts at least one of these S's, so one SI, we'll accept. Okay. If you think about it, it's the same problem before, because say M rejects S1 and rejects S2 and then accepts S3. Okay, like think of the scenario where M will accept S3 and it rejects S1, rejects S2. If we do it sequentially, it'll work, right? We run it through S1, it rejects it. We run it through S2, it rejects it. We run it through S3, it accepts it. Great. However, what if it rejects S1, accepts S3, but loops over S2? Okay? What if it loops over S2? So if we're running it sequentially, like we're trying all the strings in sequential order, I'll do S1 first. It rejects it. I'll do S2 second. It's gonna loop forever on S2, and I'll never be able to test S3 because my algorithm, it's not efficient. It loops on one of my inputs. I can never test the other one, which it might actually accept. So do you see the problem? There's a scenario where it might loop over something, and it's gonna accept maybe the right element right after it if we do it sequentially. So because of similar problems as the previous question, we can't do sequential testing, meaning, for example, I'll just repeat what I said. If M accepts S3 but loops over S2, we will never reach S3 and accept if we are testing sequentially. So first testing S1, then S2, then S3, etc. That won't work. Okay, great. So I guess that's it. We just have to think. We have to think of a way to do it in parallel or at the same time, etc. Okay, let's do that. So the idea is something like this. We'll call it, say, R, because it's a recognizer. So on input M is a Turing machine. Repeat the following. For I is 1, 2, 3, etc. We're still gonna go over everything, right? Like imagine this is some sort of for loop, and I'm saying I is 1, 2, 3, etc. These are gonna be like the indices of your strings, right? Now, before our algorithm would have said something like, "Oh, run m on si if m accepts, r accepts," like we accept. That won't work because what if it loops on one of them? So we want to modify this. What we'll say instead is run m for I steps on each input S1, S2, S3, all the way till Si. If any computation accepts, accept. Okay, that's it. What's the difference? So what are we saying here? Well, say we accept the string S4 in this scenario, okay? Say we accept the string S4. What we're going to be doing is, when I is 1, we run S1 one time, so one step. When I is 2, run S1 2 steps. Why 2 steps? That's just what we were saying, like run m or I steps on the inputs up to the index I. So we're saying that we want to run it for 2 strings, and each string we want to do it twice. So also run S2 for 2 steps. Finally, or not finally, if I is 3, same thing, run S1 3 steps. Then S2, then S3 also are going to be run 3 steps. And again, we're assuming so far, like in the scenario, that, oh, I'm going to be accepting S4, right? So finally, when I is 4, what we'll be doing is running S1, S2, S3, S4, 4 steps. Now you might tell me, hey, what if I need more steps to accept S4? Like we agreed S4 is gonna be the string that you're gonna be accepting. So I reached it. Right now I reached it, and I'm running it for 4 steps. But what if I need more? Well, like what if I need some, say 17 steps to accept S4? That's fine. I don't have to accept it once I reach it, because then the next run, when I is 5, I'll be running S4 5 times. And I might be running S5, which is unnecessary, but like I'm now running S4 more times. And when I is 6, when I is whatever, until I reach the number of steps necessary to accept S4, that's gonna happen. So 2 things that are important in this method. The first thing is that you're gonna reach the string that you're gonna be accepting, and 2, you're gonna be running it the number of times necessary. You might say, what if there are more steps than necessary, right? Like, okay, like say you're gonna be you'll accept S16, but you only need 4 steps to do so. That's okay. When you reach the index I16, you're gonna be running S16 16 steps. You only need 4, right? That's okay. Once you reach like the 4th step, it's gonna like terminate and accept. If any computation accept, then you'll accept. You don't have to run the full 16 steps. If you need less, you'll just use less. So it's a recognizer. Why is it a recognizer? Because every possible string, you're gonna go through it eventually, and you're gonna be running it enough times if need be. So we're gonna keep, but however, like when I say every possible string, there are infinitely many strings. Like I can't ever finish them. That's why it's only a recognizer. If one of the strings from S1 till S infinity, if some SI does get accepted, you'll be able to accept it, because eventually you'll reach it, and eventually you're gonna do enough steps on it. So you're gonna accept it. But if there is no string that you accept, then you're going to be looping forever, okay? You loop forever if you never accept any string. And you can't know if I should say no or not, okay? So maybe we can ask, why is the previous algorithm only a recognizer and not a decider? Well, if there is some string that can be accepted by M, we will reach it, and eventually we will run it enough times. But if M actually doesn't accept any string, we will loop forever. And the reason we can't say no, or we can't make this a decider, because you can't tell, we can't know if M doesn't accept any string or it simply hasn't reached the string that it will accept yet. Okay. So again, back to the scenario. We first tried S1 one step, then we added S2, and now we're doing each 2 steps, then S3. Then say we reach S9999, like a really big number. And so far in our algorithm, we're running this for 99999 steps, and this for 999 steps, etc. until we reach this one. We do it also for 99999 steps. And we've been doing it for a long time. So you might say, oh, it's probably not going to accept any string. But you can't say that, right? Because what if the very next string that you're going to reach, right, like S99999, 1, or like however the next number is, plus 1, what if that thing is going to be the one that gets accepted? Like you've been trying for so long, you can never know if, oh, I'm not going to accept, or like the very next string is actually going to be the one that be accepted. That's the thing with the recognizers, the reason why we can never say no. Because we don't know. We'll be able to say yes correctly. We might say no correctly, but not always, because there's that chance that what if I'm looping forever? Okay. So that's it for this one. Moving on to the next. So here we have the cool idea of reducibility. So far with our problems, we've actually been using reducibility, but maybe not in its, maybe it's not as intuitive as it might seem. So if A is mapping reducible to B, and B is a regular language, does that imply that A is a regular language? So just to refresh your memory, mapping reducible means this. If a language is mapping reducible to another, that will happen if there is a computable function where if there's something that gets accepted by the first one, then the mapping will also be accepted by the other language. Okay, that's a bit confusing. So if something gets accepted by A, and you're able to prove that's equivalent to saying that your mapping will also be accepted by B. So imagine you have some set, and you're saying, oh, if W belongs to A, my mapping is saying, so maybe I've made a function that changes it, and that mapping will also be accepted by W. Oh, by B. If you're able to make such a mapping, such a function, then great. You're able to reduce the two things. Now, this is just the function. There's also like the computable part, which is the following. So a function is said to be computable if there's a Turing machine that's able to compute f. That is to say, when M takes as input W, and M stops, the content of the tape is going to be f of W. So if there's a function, or if there's a Turing machine, so this function this mapping that's gonna happen, in order for it to happen, there has to be some Turing machine M that you give it W as input. And when this machine is done, you'll get as an output f of W. So imagine you just got W as input, maybe it's zeros and ones, and f of W just made them x's and y's. Okay? So there needs to be a Turing machine that will be able to do this transition in order to have a mapping reducibility. So two things, you need the actual mapping, and you need a Turing machine that will be able to execute that mapping. And that's technically what we've been doing all this time. Like, imagine every decidable problem that we ever did, like with EQ, DFA, and all that. So for example, usually what we'd say is we'd make EQ, DFA. We know that it's something decidable, so we put it on the right. And they give you some sort of new language to work with. Instead of proving that this language is decidable from scratch, what we do is we make a mapping where we'd be using EQ, DFA. So it does all the heavy lifting for us. So we do something that we know is already decidable, so we can become decidable. But anyway, back to this question. They're saying if B is a regular language, does that imply that A is a regular language? Now, this does remind us of another rule that we've seen before that says, oh, if B is actually decidable and A is decidable, then, if A is mapping reducible to B and B is decidable, then that must mean A is decidable. And again, that's what we've done before with decidable problems. We know that EQDFA is decidable, so we use it to build A, and A becomes decidable. We just do it. We just did it without really knowing what we were doing. Okay, so if for decidability it works, but does it work with regular languages? So you can pause a moment to think about it. The answer is actually no. For regular languages, it doesn't work. Why? Well, we'll take a counterexample. Say we have this language. Say we have A is 0n, 1n, such that n is greater than or equal to 0, such as the language of 0 and 1n. We know that this is what? We know that this is CFG, right? There is a PDA, a pushdown automata, that'll be able to decide or be able to make this. Since it's a CFG, it's obviously decidable. Well, just like a remark. And then I'll make the other language be B, and I'll only gonna make it 1. It literally only has the one element, which is 1. So this language is obviously regular. And you can see what I'm trying to go here. I'm trying to go with a counterexample. I'm gonna prove that A is mapping reducible to B. According to what they're saying here, oh, if A is reducible to B and B is regular, then A should be regular. But from the example that I've given to you, A is a CFG and B is regular, but A is still a CFG. Like, that doesn't make a regular language. Now, I have to actually build this mapping reducible. So two things. I have to build a function, and I have to prove that it's computable. So step one, let's build this function as follows. F of W. I'll make it be the following. 1, 0. So I'll map it to two things, to 1 or to 0. I'll map it to 1 if W belongs to A. I'll map it to 0 if W does not belong to A. Why these two things? Why am I doing it in this format? Well, to prove that the mapping works, the mapping reducible, we have this rule we have to abide with. If W belongs to the first language, it has to the mapping has to belong to the other one. So when I'm starting in my first set, if there's anything that does belong to A, like say I have 0, 1 that belongs to A, I'm mapping it to the element 1 that does also belong to B. Anything that belongs to A has to be mapped. So 0, 0, 1, 1, 1. Equal number of 0 equals number of 1s. Anything that belongs to A has to be mapped to something that belongs to B. It just happens to be I'm mapping them all to the same element. Nothing's stopping me. And remember, you ever have a function that's doing this. So if 0, 1 belongs to A, and this is like your W, f of W is becoming 1. So I'm mapping things that belong to A to 1, which belongs to B. And more importantly, not more importantly, but something that's also important, if something doesn't belong to A, like 1, 0, since 1 came before the zeros, this doesn't belong to A, it should also be mapped to something that doesn't belong to B. So f of W is going to be 0. Anything that doesn't belong to A, so like starting with 1, then zeros, or like alternating, or not an equal number of zeros and 1s, they should all be mapped to something that's not in A, because that's what the equivalent here means, or the if and only if. W belongs to A means f of W belongs to B, and at the same time, if W is not in A, then that must mean f of W is not in B. That's how the whole if and only if works. Okay, so we made this mapping. It's a mapping, it's a function. Is it computable though? Like the first definition, 5.20, it's correct. We mapped it correctly. But is the second part, is it computable? Is there a Turing machine that takes as input W and it'll be able to give you f of W in the way that we made it? And the answer is yes. Why? Think about it. A is a CFG, so it's definitely decidable. Any context-free grammar is definitely decidable. It's like there's definitely a Turing machine that'll be able to solve the problem that is 0 and 1n. Will you be able to create for me a Turing machine that'll check for you if 0 and 1n, like if I have an equal number of zeros followed by an equal number of 1? Yes, you can make a Turing machine for that. Can you then output either 0 or 1? Like this is the whole thing we're asking from a Turing machine. First, check for me if you are 0 and 1n. If you are, then put a 1 at the end of the tape, like when you're done. If you're not, so if you are, you do this. If you're not, then you just put a 0. Okay? I'll repeat this. So first, we created the mapping, and it works because we respected the rule that says W belongs to A if and only if f of W belongs to B. Then we had to prove that this mapping is computable, and it is, since A is a CFG, so it is decidable. You could have stopped here, and that's enough, but I'll add a bit more. Meaning, there is a Turing machine that will be able to check if W is 0n, 1n. And if it is, it will simply write 1 on the tape. And if it is not, it will write a 0 on the tape. We've done a Turing machine that's harder than 0 and 1n. So we can definitely do a Turing machine for it. Harder in the meaning it's just more, it takes more maybe states and whatever. But we're able to do that, and if it's true, we'll write a 1, otherwise we'll write a 0. One last maybe attempt to explain this. Imagine you have 0, 0, 1, 1. This does belong to A. So how, an example to do this, I put here an X, I go here, X, I go back, X, I go back, X. There's a way to do this, and it's all X's, so it does belong. Then at the very end, I'll remove all the X's, write maybe blank, 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 and for the last X, I just write a 1, and that's it. I started with 0, 0, 1, 1, and I ended up with 1. On the other hand, if they're not the same, like 0, 0, 1, x, and x here, then I go for the other one, and I notice, oh, I don't have enough zeros, so after some grind, I'll just put a 0 at the end. That's the whole idea. You start with a tape, you're ending with the other one. Okay, and hopefully that one made sense. So 2 things, you have to come up with a mapping, and then you have to prove that it's computable. And that's, again, technically what we were doing with every question about decidability. That's technically what we've been doing. Now, one more. Show that ATM is not mapping reducible to ETM. In other words, show that no computable function reduces ATM to ETM. Now, this is actually easier than the previous question. They're saying, hint, use proof by contradiction and the facts that you already know about ATM and ETM. So since they're saying proof by contradiction, we assume what we're trying to prove is actually right. So they're saying prove that it's not mapping reducible. We're gonna assume this, that ATM is actually mapping reducible to ETM. And then we reach some problem. But just before we do that, a reminder that this theorem, if A is reducible to B and B is decidable, then A is decidable. We've talked about this today. There's actually another theorem that's very similar. The difference is, instead of saying decidable, like, they replaced it with Turing recognizable, and it also works. Okay, also works. So if you are able to reduce A to B, and if whether B is decidable or Turing recognizable, A is gonna follow the same thing. So they're saying that ATM is not mapping reducible to ETM. And maybe the reason for this, by the way, is they did say use the things that you know about those 2 languages. Like, they're both not decidable, but there's more than just not being decidable. ATM is recognizable. ATM is recognizable. ATM is the language where there's Turing machines that accept a certain string. So you just run it, and if they accept, you accept. However, ETM, we just proved that ETM is obviously is definitely not decidable, and we just proved that it's co-Turing recognizable. So the complement is actually recognizable, which must mean that it itself is not recognizable. And that's really the reason why you can't reduce them, because if you did, you'd maybe that's not the reason. Maybe you could map it. In this case, you can't, but we'll prove why we can't. But this is like to give you a hint. Like, oh, maybe if something is recognizable, maybe you can't reduce it to something that's not recognizable. But just to give you an idea why ETM is not recognizable, we actually saw this before, right? If a language and its complement are recognizable, then that must mean the language is decidable. So if this is recognizable and the complement is recognizable, the language is decidable. For ETM, we just proved that the complement, a second ago, we proved that the complement is recognizable. We know that ETM is not decidable. Why? Think about it. It's like the halting problem and the ATM problem. You can find a paradox. So we know that ATM is not decidable, and we know that the complement is recognizable. That must mean that ETM is not recognizable. Because if it was, the whole thing should have been decidable. Okay, so if you know that you're not decidable and like a part of you is recognizable, then that mean the other part is not. Anyway, back to the proof of this part. Well, okay, so how are we going to do that? Well, first we're starting with the assumption, right? ATM, suppose ATM is mapping reducible to ETM. via some reduction. So I'll say via reduction f. I'll name the function that actually does this reduction, this reducibility. We'll name it f. This means W belongs to ATM. What? Remember the mapping rule. W will belong to the first language if and only if the mapping, so f of W belongs to the other, which is ATM. However, since we're talking if and only if, we could actually say this is equivalent to W not being an ATM if and only if f of W is not an ATM. Which again is equivalent to what? Saying that the complement of ATM is mapping reducible to the complement of ETM. You can add an extra line that says, oh, W belongs to the complement if and only if W belongs to the complement. And then you'll reach this part, that the complement ATM is reducible to the complement of ETM. But why this part? Why do I want to reach here? Again, let's use the facts that we know about ATM and ETM. We know that the complement is recognizable. We just proved it in part 1. We know that this one is not recognizable. We know this. However, using theorem 5.28, they're saying, oh, if something is reducible to another thing, and the one on the right-hand side is recognizable, then that must mean that the left-hand side is recognizable. That must mean we can conclude that ATM complement is recognizable, and this is the contradiction. Okay? ATM complement can't be recognizable. We know that it's not, because if it was, the whole thing ATM would be decidable. Now you could ask me, hey, why didn't we do this from the beginning? Well, from the beginning, what did I have? From the beginning, I started with ETM. I know that it's not recognizable. And I know that ATM is recognizable. But I can't conclude anything from that. The theorem says if the right-hand side is recognizable, you can conclude that the left-hand side is as well. But if the right-hand side is not, you can't really say anything about the left. Just because you reduce something from the left to the right, and if the right is not recognizable, that doesn't mean the left isn't, right? Like, just these are the two theorems you have. And they both work on where the right-hand side is something, so you can conclude the left. And the right-hand side has to either be decidable or Turing recognizable. Okay. So that's for this part. We're left with these two questions. Okay. Let's do the first one, and we'll leave the second one for next time. So let's do 5.22. Show that A, again, like as you noticed, like from these last few questions, from maybe part 2, part 3, these two, where it's more focusing on the reducibility of these problems. Technically, we've been using these mappings, even like in undecidable problems, we've been using these mappings. We just assume something and we reach a contradiction, but we've never been implicitly writing it in this way. Anywho. 5.22. Show that A is Turing recognizable if and only if A is reducible to ATM. Now, one idea when you see if and only if, you could prove it in two directions. Like you could prove it in this direction and then in this direction. So you get one part as given and the other part you have to prove. So in this, like in the first scenario, the way that I wrote this arrow, the thing on the left-hand side is given, and I want to prove the left-hand side. So it's given that there are reducible. I have to prove now I have to prove that A is Turing recognizable. So this part is actually easy, right? If you're given that A is reducible to ATM, and we know that ATM is recognizable using the previous theorem, we can just say, so remember, if the right-hand side is recognizable and you have a reducibility, we can simply deduce that A is Turing recognizable. So that was quick. Let's try now the other way. So we're given that A is Turing recognizable. Can I find a mapping between these two? So I know now that A is recognizable. Can I find this mapping? What do you think? What could we do in this scenario? Well, let's see. Let's see if I can come up with a function. A is Turing recognizable, right? Say M, let M be the Turing machine that recognizes A. Okay? That recognizes A. Meaning W belongs to A if and only if M accepts W. Makes sense? Like A is your language. It'll only, a string or an input will belong to this language if and only if the recognizer of this language accepts this string. But does that look something very similar to something that ATM must do? So we'll do the following. My mapping, I'm going to call it something like this. It'll take W, and it's going to do this thing, and then make it a couple with the Turing machine. I can do that. So, like, what am I saying, like, with this mapping? All I'm saying is, if W is in A, so like I'm going to repeat the part that I wrote down there. W is in A if and only if M accepts W, which is true if and only if M accepts W. So you tell me, if and only if when. I want to reach, eventually I want to reach on the right hand side that f of W belongs to ATM. That's the whole point. If you started with W is in A and we reached that f of W is in ATM, that's it. We made the relationship. We might have to prove that it's computable, but in this scenario, that part might be easy. So let's repeat. W is in A if and only if M accepts W. Why this part? Because M is a recognizer for A. So it'll be able to correctly tell you yes. It doesn't know what to do for no, but for yes, it'll correctly tell you yes. So it's a recognizer for A. Now this happens if and only if this couple, MW, belongs to ATM. Do you agree? Like, when does M accept W? This is as if you're saying, oh, if MW belongs to ATM. Why? Because ATM is the language that says, oh, M accepts W. And finally, like, just one more word, if and only if f of W, like what we wrote down there, f of W belongs to ATM. That's it. We started with something and we reached the end result. It works. And so that's your mapping. And for the computability part, it's fine. Like the whole thing, we started with it being recognizer. So obviously there is a Turing machine that does this. It's pretty trivial. Just to let you know what we're doing here. We started with the language A. Literally, this is what we're saying. We're saying W, if it belongs to A, we're making a mapping. It's equivalent if FFW, which is a couple MW, if this thing belongs to ATM. Can you see how like obvious it is? W belongs to A if and only if MW belongs to ATM. Like you're saying, oh, there's two ways you could solve this question. There's two ways you can check if W belongs to A. Either use the Turing machine and just run M on W, right? You can just run M on W, and if M accepts, you'll accept. And you'll know that W is an A. That's one way of solving the issue. Or run MW, or say R decides ATM. Run R on MW, not decides, recognizes. Where R is a recognizer for ATM. 1 and 2 literally both mean the same thing. To know if W is in A, you can either run M on W, like the machine M that recognizes A, run it on W, or you get the whole machine M and you get the input W, and you run that on some other machine R that recognizes ATM. They both mean the same thing, because in the description of the decider of ATM, it's just going to be running M on W. It's the same thing. Okay, hopefully that made some level of sense. You could repeat everything we mentioned today and think about maybe 5.23. How could you do that? Because it's very similar, but not instead of recognizability, we're talking about decidability. So maybe in this scenario, you'd have to make a more physical mapping, something like what we did over here with this question about, if you remember it, A is regular, B, or A is CFG, B is regular, that whole thing, something similar to that. But okay, see you in the next and last one. Goodbye.